Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, Evaluate Division. So the problem here is that we have an array of variable pairs that are basically equations, and then we have another array for the values of these equations. So for example, we get equation for A and B, and the value at the same position, then the I in equation and the value in the same position in values, they represent that the equation A divided by B is equal to the values at position I. Okay, and then we get a list of queries that has two variables C and D, and then what we want is to get the value of that equation C divided by D. Okay, and if there is no answer, so basically there is, from these equations and values, we can't obtain the value for the query, we want to return -1. And so that's the problem here. And we are told that the input is always valid, which basically means that we don't have a division by 0, because then there is no real answer, and there is also no contradiction between the equations. Okay, so if we take a look here at the first equation, AB, this means A divided by B is equal to 2, and B divided by C is equal to 3. And so the queries that we have here are A divided by C. Okay, so how do we get A divided by C? Well, A divided by C, we already have A divided by B and B divided by C. And so you could sort of think of it like going through a path from A, B, and then from B to C. But how do we get that? Well, with the multiplication, if we multiply these two, we will get rid of B and it will cancel each other out, and we are left with A divided by C, which is exactly what we want. So this tells us we can just multiply this and this to get the value, which is 6, right? And so that's what we have here, so we return 6. What about B divided by A? Well, B divided by A, we already have A divided by B, right? So if we want to get B divided by E, we can just say 1 divided by this, right? This is the result of this would be B divided by A, and so that means basically 1 divided by 2.0, and so that's 0.5. So that's sort of the idea here. Now the other query value we have is A to E, A divided by E, but we don't have E in our equations here, so we return -1 because there is no answer. The other thing to note here is that we also have the A divided by A, so the same values. In that case, we want to return 1. But if it doesn't exist even in the equations we have, we want to, like X here, we want to return -1. Okay, so pretty simple here. Now, if we look at the constraint, is up to 20 equations. So it should be easy to do an event or even an event squared pass. And we only have lowercase English letters and digits. Okay, so let's see how we can tackle this. Okay, so let's see how we can tackle it. Well, from the example we saw earlier, that actually gives us a hint, right? Because so A divided by B, we had that it's equal to 2.0, and then B divided by C, we had that it's equal to 3.0. Okay, and so when we wanted to get A divided by C, well, this we said is just A divided by B multiplied by B divided by C, right? And so that this pretty much just gives us, we take the values of these, which is 2 and multiplied by 3.0, right? So this gives us 6.0. And this can extend, like, let's say we had also D divided by E, which equal maybe to 4, or maybe to 2.0, just to simplify our, okay? Then A divided by E, for example, would be, let's actually do C divided by D here. So C divided by D, then A divided by C would be A divided by B multiplied by, so D here, A divided by B multiplied by B divided by C multiplied by C divided by D, right? Because we will get first A divided by C here, so this is C, and then if we multiply C divided by D, we'll get A divided by D, right? Which is what we want here. So we can just multiply all these 3, which will give us 2.0 multiplied by 3.0 multiplied by 2.0, right? Which would be 12. 6, 12, okay? And so you can see here, this extends, right? No matter what the equation length you have, right? And so this makes you think about a graph, right? Because that's exactly how a graph works, right? You have a node, right? And then you go from that node with some cost, and then from that node you go here, and then you go to another node. Let's call this x1, x2, x3, x4, right? So this is cost 1, cost 2, cost 3. And depends, like, usually this cost, how do you combine it, right? In some cases you might combine it by doing the sum, but in this case we want to combine it by just multiplying. Okay, so what ends up being is that if we get, let's say, a divided by d, we just want to go to the path from a to d, right? And then while we are doing the path, for each cost we'll just multiply them, right? And so that's what we'll do here. We can do BFS or DFS to do this. I think it's easier with BFS, so we'll just proceed with that. Now, the other thing to note here is that, okay, so we have this a divided by b, but there was another case, which is we got b divided by a, right? And we said that this is just 1 divided by a, b, because that's the same thing. And so we can just 1 divided by the cost of c1. So how do we bake that into our graph? Well, we can just, when we are constructing the graph, for each equation we have, we can just add another node, make these directed, right? And then add another node here and say the cost is 1 divided by the cost that we, the cost from the equation. So we just reverse. So here, since we have a node from A to B with a cost of 2.0, we'll create another node from B to A with the cost 1 divided by this cost, which is 2.0, which is basically 0.5. And we'll do this for every equation. That way, even if there was, let's say, c divided by a here, right? This is just the cost of a divided by c, okay? Or you could think of it as also the cost of c divided by b multiplied by b divided by a, right? Because then you could just move these like this, you get c divided by a, and cb, that's just 1 divided by 3.0, and BA is just 1 divided by 2.0, right? So you could do it whichever way we want. Okay, so now we know how to do it with for the cases where you have something that is compounding like this. In the case where it's the reverse, so like b divided by a, where we just have to do 1 divided by ab. Now the other case is, what if the node is not in the graph? Well, if the node is not in the graph, let's just return -1.0. So we can just do an explicit check for this. And then one more case, which is, what if the values are the same? So let's say we get a divided by a, and a is in the graph. Well, in that case, we just want to return 1. Okay, so if basically when the source is equal to the destination, we just want to return 1. But this is actually, you could just leave it to do leave the default BFS, because the default BFS, you will start with the source and with the cost, which would be initially just 1, so that multiplication works. And so the first pass of BFS will check if we reach the destination. And since the source is equal to the destination, we'll reach it and we'll just return that cost, which would be 1 here, okay? Because in our BFS, we will want to add the node and the cost so far, which would be each time we traverse an edge, we'll just multiply. That's what we said earlier here, okay? That we will multiply the costs. And that's pretty much the idea here. We'll proceed and use BFS in this case. And in terms of time complexity, is the number of edges plus the number of vertices. This is at most like double the number of equations, right? Because we do this reverse thing. So in terms of time complexity, it's just, you know, in the order of length of the equation. Let's call that maybe n. And then the values are just the nodes themselves, which are just the values in the equation. And so this is also double the number of equations at most. And so that's also n. So overall, it's O of n time. Okay. And then for space, similar, O of e plus v, because we will use a q for BFS. So it's O of n as well. Yeah, so let's code this up and make sure it passes. Okay, so let's implement the solution we just saw in the overview. So what do we need? So we need to define BFS, right, with the source and destination. We will fill it up later, right? But what we need is first to also create our graph. So this would be just a default dictionary with the default values list. where basically for each one we'll have the node and its neighbors, and each neighbor would have the neighbor and the cost associated, and we get these from the equations. Okay, and so our equations are A, B in equation, but since we want to get the value of each equation, we want to get the position, and so we want to enumerate here. So that would be something like this. Okay. And then for our graph, we said that A, we will need to give, this is the neighbor, right? But the value is in values I. And we said that if you have A divided by B, we want to record both the edge A to B with the values I, but also the edge B to A with the values, which is 1 divided by the values of I, right? And so that's what we'll do here. So we'll just take this, and this would be B, and this would be A, so the reverse that to get this edge, and this would be 1 divided by that. Okay, so that's what we do there. And then now we need to start doing our queries. Okay, so since the number of equations is at most 20, and I think the number of queries is also similar. Yep, and so we can do BFS for each query. It shouldn't be bad. So we'll just do our BFS for A and B, and we need the result that we'll return and add the values to that. Okay, and this is what we'll return at the end. And now we can do our BFS. Just first we want to handle one case, which is what if the node is not even in the graph, right? In that case, we want to just return -1. Okay, and now we'll start our BFS. So we need the Q. Let's call this DQ, and we need the source node, and then 1 because we will multiply. So we use 1 is the so that the multiplication works. And now we'll just do normal BFS. So we'll pop from our Q with a node, and we will get the cost. And then we want to check in BFS if we reached our destination. If we did, we just return that cost, and then we go through the neighbors. And then for the neighbors, we want to go through the neighbors in the graph. For that node, we'll get the neighbor and the cost for this neighbor. And so we want to add that to the queue so that we process it next. So we need the neighbor and this cost for this individual neighbor, because this cost is just from you to this neighbor, right? But we want to also count the previous cost. And we said we aggregate the cost by multiplicating them. Okay, so that's why we multiply them like this. And then if we didn't find any path, we want to just return -1 because that's what the problem asks us to do. There's just one thing we haven't done yet, which is we need a visited set so that we don't visit the same nodes multiple times. So we have a visited set here, and we want to add to it. So we're going to add the node, and then here we want to make sure that this is not visited before visiting it. And now we should be good. And looks like it gets accepted, and that passes. Yeah, so pretty simple BFS application. The main insight is this here, knowing how you can first knowing that you can represent it with a graph, right? And the cost, you can just multiply them. And then the second insight is that you can divide by 1 to get the reverse edge. Yeah, that's pretty much it. Thanks for watching, and see you on the next one. Bye.